Solar power is energy from the sun. It's a clean and sustainable alternative to fossil fuels. Solar cells, also known as photovoltaic cells, are the devices that make this energy conversion possible. They capture sunlight and convert it into electricity. However, the amount of power generated by a solar cell is not constant. It changes with the position of the sun in the sky and the temperature of the solar cell itself. The angle at which sunlight hits a solar panel is crucial. This is called the angle of incidence. Imagine sunlight as a stream of tiny energy packets called photons. When these photons strike the solar cell directly, more of them hit the surface. This results in higher energy absorption and more electricity production. Conversely, when sunlight hits the panel at an oblique angle, fewer photons reach the surface, leading to reduced power output. Understanding these variations is crucial for optimizing solar energy systems. The angle of incidence directly influences the amount of sunlight and, consequently, the number of photons that reach the solar cell's surface. A steeper angle means less light is captured, reducing the cell's electricity generation. Conversely, a more direct angle maximizes sunlight capture and boosts power output. This relationship between the angle of incidence and power output is quantified using a parameter called the incidence angle modifier, IAM. Temperature also plays a crucial role in solar panel efficiency. Solar cells have an optimal operating temperature range. As the temperature rises above this range, their efficiency in converting sunlight to electricity decreases. This is because the heat causes increased movement of electrons within the cell. This heightened activity disrupts the smooth flow of electricity, resulting in lower power output. Conversely, cooler temperatures can slightly improve efficiency up to a point, beyond which further cooling has negligible effects. Understanding both the angle of incidence and temperature effects is paramount for maximizing solar power generation. The sun's position in the sky is not static. It constantly changes throughout the day and across seasons. This dynamic movement directly impacts the angle at which sunlight strikes a solar panel, known as the angle of incidence. As the sun rises, traverses the sky, and sets, the angle of incidence continuously changes, leading to fluctuations in solar power output. At solar noon, when the sun reaches its highest point, the angle of incidence is at its minimum. This results in the maximum amount of sunlight hitting the panel's surface, leading to peak power generation. However, as the sun moves away from its zenith, the angle of incidence increases. This means a smaller portion of sunlight hits the panel directly, causing a decline in power output. To address this continuous change, solar trackers are often employed. These devices adjust the panel's orientation throughout the day, ensuring it remains perpendicular to the sun's rays, thereby maximizing energy capture. The geographical location of a solar panel plays a crucial role in determining its energy output potential. Latitude, the angular distance of a point from the Earth's equator, significantly influences the average angle at which sunlight strikes the Earth's surface. Locations closer to the equator receive sunlight at angles closer to 90 degrees, resulting in higher solar irradiance and greater energy potential. Conversely, as we move towards the poles, the angle of incidence becomes increasingly oblique. This means the same amount of sunlight is spread over a larger area, leading to lower solar irradiance and reduced energy potential. For instance, solar panels in regions with high solar irradiance, such as deserts, can generate significantly more electricity compared to those at higher latitudes. Understanding the impact of latitude is essential for optimizing solar panel installation. To maximize energy capture, solar panels are often tilted at an optimal angle. This angle varies depending on the latitude of the location, ensuring the panels receive sunlight at the most direct angle possible throughout the year. Section 3. Beyond the angle. While the angle of incidence is a critical factor influencing solar panel output, it is essential to acknowledge that it does not act in isolation. Several other variables, often interacting in complex ways, can affect the overall efficiency of a solar energy system. These factors include transient weather patterns, atmospheric conditions, and potential shading issues. Cloud cover, for example, can significantly reduce the amount of sunlight reaching the Earth's surface, directly impacting solar panel output. Similarly, Atmospheric conditions, such as air pollution and humidity, can scatter and absorb sunlight, further reducing the amount of energy reaching the solar panels. Moreover, shading from nearby trees, buildings, or other obstructions can cast shadows on solar panels, significantly hindering their performance. Therefore, when assessing the performance of solar energy systems, it is crucial to consider the combined impact of these various factors. Understanding this complex interplay is essential for accurate predictions and efficient system design. However, beyond the angle of the sun and these other factors, temperature also plays a critical role in dictating the efficiency of solar cells. Section 1. The heat is on. While sunlight provides the energy source for solar panels, temperature plays a crucial role in dictating how efficiently this energy is converted into electricity. Solar cells, like any electronic device, are sensitive to temperature fluctuations, and their performance can be significantly impacted by the heat they experience. As the temperature of a solar cell rises, its efficiency in converting sunlight to electricity decreases. This inverse relationship between temperature and efficiency arises from the fundamental physics governing how solar cells operate. Solar cells are made up of semiconductor materials, typically silicon. When sunlight strikes these materials, it knocks electrons loose, creating an electric current. However, the movement of these electrons is also influenced by the ambient temperature. As the temperature increases, the electrons within the solar cell become more agitated and move around more randomly. This increased thermal motion disrupts the smooth flow of electrons, making it harder for them to be channeled into a usable electric current. This phenomenon is quantified by a parameter called the temperature coefficient, which describes the percentage decrease in power output for every degree Celsius rise in temperature. Section 2. Finding the sweet spot. Just as there's an optimal angle for sunlight to hit a solar panel, there's also an optimal temperature range within which solar cells operate most efficiently. This sweet spot typically falls within a relatively narrow band, usually between 20 to 25 degrees Celsius, 68 to 77 degrees Fahrenheit. As temperatures deviate from this ideal range, either too high or too low, the efficiency of the solar cell begins to decline. At high temperatures, as discussed earlier, the increased thermal motion of electrons hinders their efficient flow, leading to reduced power output. On the other hand, while cooler temperatures might seem beneficial, they can also negatively impact performance. At very low temperatures, the materials used in solar cells can become less conductive, again hindering the flow of electrons. This sensitivity to extreme temperatures poses significant challenges for solar energy systems, particularly in regions with harsh climates. Desert environments, for example, experience scorching daytime temperatures that can drastically reduce solar panel efficiency. Conversely, in extremely cold climates, solar panels may suffer from reduced output during the frigid winter months. Section 3. Keeping it cool. Given the significant impact of temperature on solar panel performance, mitigating these thermal effects is crucial for maximizing energy output. Various cooling techniques have been developed and implemented to maintain solar panels within their optimal operating temperature range, even under challenging environmental conditions. These techniques range from passive cooling methods, harnessing natural processes, to active cooling systems that require external power. Natural convection, a passive cooling method, relies on the natural airflow around the solar panels to dissipate heat. This can be enhanced by elevating the panels, allowing for better air circulation beneath them. Active cooling systems, on the other hand, employ fans or pumps to circulate cool air or liquids around the panels, actively drawing heat away from the cells. Beyond cooling techniques, the design and materials used in solar panels also play a crucial role in temperature control. For instance, using lighter-colored materials for the panel's backsheet can help reflect sunlight and reduce heat absorption. Additionally, incorporating heat sinks or other thermal management materials within the panel's structure can aid in dissipating heat away from the solar cells. As technology advances, researchers are constantly exploring new materials and designs to improve the thermal performance of solar panels, further optimizing their efficiency and longevity. Section 1. The science of catching more light. The incidence angle modifier, or IAM, is a crucial parameter in solar energy that quantifies how effectively a solar panel captures sunlight at different angles. It represents the ratio of power output at a specific angle of incidence to the power output when the sunlight hits the panel perpendicularly. Understanding IAM is paramount because the angle at which sunlight strikes a solar panel constantly changes throughout the day and across seasons, influencing the overall energy output. IAM is typically represented as a curve that illustrates the panel's performance at various angles of incidence. The shape and characteristics of this curve depend on the specific design and materials used in the solar panel. Generally, IAM curves show a gradual decline in power output as the angle of incidence deviates from the perpendicular. However, different solar panel technologies exhibit variations in their IAM curves. For instance, some panels are designed to maintain higher performance even at steeper angles, while others might experience more significant drops in output. Therefore, considering the IAM characteristics of different panel types is crucial when selecting the most suitable option for a specific location and application. Section 2. Engineering solutions for optimal angles. Advancements in solar technology have led to innovative solutions for enhancing IAM and maximizing energy capture even when sunlight strikes the panel at less than ideal angles. These innovations primarily focus on minimizing reflection and maximizing the absorption of light, regardless of its angle of incidence. One significant breakthrough in this area is the development of highly effective anti-reflective coatings. Traditional solar panels often suffer from significant reflection losses, especially at steeper angles of incidence. Anti-reflective coatings, applied as a thin layer on the panel's surface, help mitigate this issue by reducing the amount of light reflected away from the cell. These coatings work by creating a gradual transition in the refractive index between air and the solar cell material, allowing more light to enter the cell and be converted into electricity. Another promising approach for enhancing IAM lies in surface texturing. By incorporating microscopic textures or patterns on the solar cell's surface, researchers can manipulate how light interacts with the panel. These textures can effectively trap light rays, increasing the path length of photons within the cell and enhancing the probability of absorption. Surface texturing can be achieved through various methods, including etching, lithography, and nanoimprinting. Section 3. A glimpse into the future of IAM. The pursuit of higher efficiency in solar energy systems has fueled continuous research and development in IAM technologies. Scientists and engineers are exploring novel materials, designs, and fabrication techniques to further enhance the light-capturing capabilities of solar panels. These advancements hold the potential to significantly improve the performance and cost-effectiveness of solar energy, propelling its wider adoption as a sustainable energy source. One promising avenue of research focuses on developing new anti-reflective coatings with even higher performance and durability. Researchers are experimenting with different materials and multi-layer coatings to achieve near-perfect light transmission across a broader range of wavelengths and angles of incidence. Additionally, advancements in nanotechnology have opened up exciting possibilities for surface texturing. Researchers are exploring the use of nanostructures, such as nanowires and quantum dots, to create highly efficient light-trapping surfaces. These nanostructures can effectively scatter and confine light within the solar cell, significantly increasing the probability of absorption and boosting overall efficiency. The continuous innovation in IAM technologies is crucial for overcoming the limitations imposed by varying sunlight angles, paving the way for solar energy to play an even more prominent role in the global energy landscape. Harvesting the full potential of sunlight. The efficiency of solar panels is linked to the angle of incoming sunlight and the operating temperature. Solar trackers adjust panel orientation to follow the sun, ensuring optimal energy capture. Temperature plays a crucial role in solar cell efficiency. Researchers have developed cooling techniques to maintain optimal temperature. Anti-reflective coatings minimize light reflection, boosting efficiency. These approaches highlight the multifaceted nature of solar technology. A brighter future powered by the sun. The journey of solar energy is a testament to human ingenuity. From bulky cells to today's sleek panels, the evolution is remarkable. Yet, we've only scratched the surface. Research continues to push the boundaries of efficiency and affordability. These advancements unlock the sun's full potential for a sustainable future. By harnessing the sun, we can build a brighter future for all.